All right, so we're all back together in the same room. Comps are past us, hooray, right? So those of you who are comping, are you all done?
We have the oral exam.
I'm sorry?
We have the oral portion.
The oral portion, okay, but you're done sitting in a room dumping your brain that
12 hours.
12 hours. And hopefully you've caught up on your sleep, maybe, your laundry, your sanity. Yeah, I never had to go through a comp like that, actually. We never did it that way. So I can't relate, but I can just say, welcome back. And that means that everybody has caught up on homework 2. So I can go over that real quick just to make sure that we're all on the same page. So homework 2 was intended as a review of general linear models. It was just what I would call a simple, meaning only one type of sampling between persons, linear model with a couple of predictors in it. All of your, the fictitious data sets I'm going to give you will take place at Midwestern Red State University. I figure that covers pretty much everywhere I've ever lived. That's kind of an inside joke. No, if you think about it, Midwestern Red State, like that's all of them, right? It used to be a Midwestern Rectangular State University, but that's a little more specific. But these are all, of course, fake data, so you each have your own data set to play with. In terms of the computational questions, it looks like everybody did just fine with that. So here, these are not tricky. I'm just getting you used to where to look in the output for things so that when the numbers come back, you know what you're looking at. That's step 1 to knowing what they mean. So we had an empty model, empty meaning no predictors. We're going to have a lot more of those today when we look at alternative covariance structures. And then a model after including a couple effects of predictors. We can have significance test for the overall model. So that F has a special name. What do I call that more generally? Starts with an M and a W. Two-word phrase. M, W. M-U, W-A. M-U-L, we'll play hangman. What? Multivariate. And W-A-L, Wald, yeah. So you'll hear the phrase Wald test associated with Z's and chi-squares officially, but if you're using a finite sample approximation, so you have like denominator degrees of freedom that show up in your output, then you get T or F instead. So univariate is testing one fixed effect. That's a univariate Wald test, so the p-value that shows up for each predictor. When you test more than one fixed effect at the same time, such as the test of the model, meaning a set of predictors in this case, you can refer to that F as a multivariate Wald test. So you have a contrast statement that can be used to give that to you. You would also get it by default if you use a regression piece of software. So we have the fixed intercept in this model, and we have 3 main effects, the effects of motivation, and then 2 different versions of GRE. And the story that created this data set, of course, is that GRE verbal doesn't matter, but quant does. Hooray! I am living proof that that must be true to some extent, because I tanked my verbal, and yet here I stand before you, employed and tenured. So that's my story, and I'm sticking to it. In terms of interpreting these things, each of you figured out whether or not these things were significant and in the right direction in terms of whether it enhanced your score or diminished it. And there was a little bit of issue in terms of these questions here, main and for all persons. So I wanted to go over that. So in this model, these 4 fixed effects make up the model that we're interpreting. Fixed intercept, 3 predictors. The intercept is conditional. So we can say that a couple of different ways. Intercept by itself means conditional outcome. It's the expected outcome for ... Conditional means the for ... as opposed to just the grand mean, which is for everybody. So it's the conditional mean, the intercept, the expected outcome, however you want to think about it, predicted outcome, for somebody with a 0 value on motivation, verbal, and quantitative. And the 0 value you defined when you created those new variables based on the instructions for centering. So we centered motivation at 4, which is the middle of the scale, and then GRE, quant, and verbal were centered at this is the old version of these, 500 and 550. So in thinking about what this 60 means, This is specific to a kind of person who has a value of 4, 500, and 550 respectively. Conditional. The rest of these 3 fixed effects, because they are only main effects, because they are not part of any interactions, they are for everybody. So even though motivation, for instance, is centered at 4, this is not the effect of motivation for somebody with a value of 4. It's the effect for everybody. The "you are here" sign of the model, the intercept is 60. So 60 is what you get if you have a motivation of 4. For every unit increase beyond 4, you get another 4 tacked onto your 60. So each of these fixed effects you can think of as after controlling for the others. So that type of language, this is the unique effect of motivation after controlling for verbal and quant. This is the unique effect of verbal after controlling for quant and motivation, and so on. That language is perfectly fine, but it doesn't mean that these fixed effects are specific to certain kinds of people. They are not yet conditional. They become conditional when they're part of interactions. And in longitudinal models, that happens pretty quickly. The extent to which people change differently over time is going to be a time by something interaction. So the correct answer for all of these is a main effect that holds for all persons. So any questions on that? Okay, any questions on homework 3? Let's see. While I'm up here. Has anyone started? It's due Friday. You got a few days. It's okay if you haven't. I just want to ask if you want to talk about anything while I'm here. No? Okay, good enough. Then we'll move back into the stuff we were talking about last time. So we were talking about what last time? Tell me what you remember. I will accept words, letters, gestures, anything.
Talked about pants.
Pants, yes. Pants were my, is it analogy or metaphor? I don't know.
This is extended enough. I would call it a metaphor.
It's a metaphor? Pants is a metaphor? For
fitting, for modeling different types of variance across time, or different
Yes.
strategies to model variance.
Yes, so variance and covariance across time. So the idea that the pattern of information that we have in our outcome across people and across occasions is characterized by a matrix. So we've referred to that so far as an R matrix. It has as many rows and columns as you have occasions. And so we talked about different patterns that you can put into your model that hopefully mimic the patterns in the data. So what are the loosest fitting pants in my analogy here? Nowadays you would call them maybe athleisure as opposed to sweatpants, but that was the term I'm sticking with is sweatpants. They always fit, right? You don't ever have to worry about misfit with sweatpants. You can always fit in them. What's the analogy?
These ones were unstructured.
Yep, that's unstructured. Let me get out, instead of writing on the board, I'm gonna write on make little tables in Excel. So all of the things that I'm writing down you have in your notes, I'm just sort of making a record of what we're talking about here. So we have pants as one heading, model. So I call these sweatpants. The model is unstructured. It will be abbreviated UN. What's in it? Parameters. What does that model say about your data, your matrix? Does it make restrictions? Does it make assumptions, restrictions, or force it to be any particular shape or pattern? Nope. So I'm going to say all of them, meaning all possible variances and covariances get estimated as separate entities. It is the data. Consequently, fit best. That's the answer key. This goes by other names, synonyms. You may have learned about this in an ANOVA class as what kind of ANOVA? I heard you say it. It's a MANOVA. It's the MANOVA version, or multivariate. The multivariate, I'm going to put out multivariate and repeated measures ANOVA. There, I need to make this whole thing wrap. There we go. This is the multivariate approach to repeated measures ANOVA. That's what it's known as. Has anyone taken SEM in here? Structural equation models? Okay, you guys get to give me another synonym. What? Latent growth model, you said? Good try, but no. Here's your hint. Best. What's the best model in SEM?
Just identified one.
The one that everything gets compared to is called saturated. Yes, saturated, or H1 is what it's called in M+ output, for instance. So yes, I'm going to do a H1 saturated. Okay, so you're familiar with the concept. So if this is the best model, why don't we just call it good and use this? It's complicated, yes, because this part, all of them. The number of parameters to be estimated increases with the number of occasions. There's a formula to figure out how many. It's number of occasions times number of occasions plus 1 divided by 2. That's the same formula with which you compute degrees of freedom in SEM. It's the number of variances and covariances. So at a minimum, you'd have to have enough people to be able to estimate all those variances and covariances. And that's before you put anything in the model that you actually care about. Now, when can't we do this at all? In what kind of data is this not even possible to try? Think about people and people not cooperating. Okay, that's one way they can not cooperate. They can just not come, right? Not come back. Attrition, missing data. And in this case, if you have any missing data, you could estimate this model so long as you use some kind of likelihood as opposed to least squares, or Bayes, alternatively, since Bayes uses likelihood as well. Ordinary least squares is the problem with missing data. So when people fit this model using ordinary least squares, that's when they use the label MANOVA that goes with it. If they fit this model using likelihood or with a prior combined with the likelihood, which is Bayes, then they use the term saturated. But in what other way can people not cooperate?
They come in different times?
They come in different times, right? You want them to come exactly 6 months later, but they're sick that day, and so they show up like 7 months later. Is that still 6 months later? Rounding time should make you feel squishy. That's my phrase. Squishy means uncomfortable to me. Things that make me feel squishy. When people wear shoes in my house, right? I just picture all the dirt and germs just all over my carpet, and it just gives me that like, I feel the same way when people tell me about rounding time into nearest intervals. You're introducing error. What are you doing? You don't have to do that. Well, to fit this structure, you do. Because there has to be a matrix that can summarize everybody's data the same way. And if you have time 2.5 and 3.5, there's nowhere to stick it. So this model is best, but it's only possible when you have balanced data. Everybody's on the same measurement schedule. And it's only possible to the extent that you have enough people relative to the number of variances and covariances that you have to estimate. While we're on the topic of ANOVA, I'm going to fill in this one here for the label. The univariate approach to repeated measures ANOVA, which I thought was the only kind up until I started teaching this stuff. What is this one? What's in it? Which one am I talking about? This is sort of the other extreme of the possible choices that we have. You can fill in any of these columns here. Skinny jeans, yes. Skinny jeans, not for everyone. They are not very forgiving. They are very restrictive. To me, they're the opposite of sweatpants. What am I talking about in terms of a prediction? What's the restriction that this model places on the pattern of variances and covariances over time?
We are trying to estimate variances, and covariances has to be symmetric.
Estimate them as what? I'm sorry?
We are trying to estimate the variances here.
Variances are what? How do we estimate them? What do we say goes into them? Do they each get to be whatever they want to be? Nope. They have what?
Error.
Two kinds of error go into variance. These are the two letters that we started off with last time. Our friends U and E. So we're talking about the phrase that's called compound symmetry. Did I spell that right? Close enough. CS. Harms, U0 variance, and E variance. So what this model says is very restrictive. All the variance, time 1, time 2, time 3, time whatever, same. The extent to which people differ from each other, same at each occasion. The reason for that variance is twofold. Because some people are just higher than average. All the time they have higher means, and the rest of it is within persons. People vary around their means. So the diagonal is additive of these two things. U0 is a random intercept, the idea that each person gets their own deviation from the grand mean. So the fixed intercept is the grand mean that everybody gets, plus U0 then gets them to their own mean. So U0 has a mean of 0 because the mean of U0 is the fixed intercept. That is, let me get out something real quick. This one. This. Fixed plus random. The notation's going to change. We're going to swap out beta for something else, but this idea of fixed plus random gets you to yours is going to stay the same throughout the semester. Fixed means the constant part that everybody gets. Random means the part that's your own. So in addition to having a grand mean that everybody shares, you get your own U0. The variance across the U0s is the model parameter, though. We don't actually care what each person's U0 is, and we don't need to know what it is. U0 is a factor score. If we're working in multivariate normal land, which is where we're at, residuals are normal, random effects are normal, we don't ever need to know what they are. We just need to know what their variance and covariance is to figure everything else out. And then from there, E picks up what's left. E is, why are you off your mean today? So back in my little thing here, U0 variance is a random intercept. That makes it level. Two choices. 2. That means E variance is level 1. Excuse me, I'm still running a cold here, so I'm going to choke on my own phlegm every few minutes. Sorry about that. Oi. Let's do the synonym game. U0 variance. Between or within?
Between.
Between. Inter or intra? Inter. That means E is within, intra, and longitudinal. So in terms of fit, I'm going to call this worst with the star. The star is because what would make this even worse if we took out U0? So if we fit a cross-sectional model to longitudinal data, if we had only E, that's the absolute worst. But nobody would do that. So the worst plausible model that we would entertain is this one. E only would be like jeggings, taking skinny jeans even tighter and less forgiving. You know what jeggings are? It's jeans that are leggings. I don't understand. But yeah. So this is the worst possible model that we would entertain for longitudinal data. So note that both of these options that we have so far are trying to do the same thing. They are trying to summarize the overall pattern that we get in a data set. Unstructured does it by just trying to give you the pattern back. Compound symmetry, random intercept only, does it by saying, well, it's because the pattern is part level 2 and part level 1. Different means to the same end. It's the overall pattern that we're after. And if all you had ever learned was ANOVA for longitudinal data, this would be the end of the list. But there's like 30,000 more options out there if you know how to ask them in software, and that's where we pick up. So, questions on this? Okay. So then what are the other options? There's two, I would say, two ends of a continuum of longitudinal data that guide you to which sort of sets of options you're looking at. Change is the left side. That's not what we're doing right now. That's next week. We're starting with the right side, which I refer to as fluctuation. It's for longitudinal data where sampling over time is just a way to get a lot of data from the same person. Doesn't really matter what time is which. We're just looking at within-person fluctuations, typically in things that don't change purposively, like stress, heart rate, sleeping patterns, mood, social support. It's the some days are worse than others kinds of studies. That's what we're talking about the models for. So here are the two choices that we just reviewed. Compound symmetry, U plus E, or unstructured. And then we started talking at the end about the other options that we have. So let me introduce some data to give us some practice with what these things would look like. So this is example 4. I have in front of you what is referred to informally as a spaghetti plot. You heard that term before? It's because if you took like a handful of wet spaghetti and just like threw it at the wall, that's what you get. Now, if you're trying to sound more formal, such as in a paper or a professional presentation, this is a plot of individual trajectories. Okay, it's not spaghetti. individual trajectories. But these are real data. That's the nice thing about having been part of 1,000,001 data analyses in my lifetime thus far, is that I have tons of real data to show you. And real data doesn't always behave itself. So would you like to hear the story behind these real data? Why not, right? I can do story time in the middle of stats class. Breaks up the monotony, the formulas, and the matrices. So this was a friend of mine, University of Kansas, her dissertation. And she was interested in studying resilience types of factors. She was a clinical psychologist, and she was interested especially in studying forgiveness and coping. And she had a dissertation proposal. She went into her proposal meeting with this nice little cross-sectional study. She was going to recruit people who had varying degrees of psoriasis, which is a skin condition. It's not catching, but it looks, it has like redness and rashes, and it's thought to be exacerbated by stress and other kinds of things. And she wanted to see if people who were better at coping, more forgiving, more resilient, etc., had different levels of psoriasis. That was her dissertation. She came out of her proposal meeting with her committee completely redoing her study into longitudinal. So that became wave one, what she had proposed. And she and her committee asked her to follow people for 8 weeks and ask them to get weekly ratings of things like stress and how bad their psoriasis happened to be each week. So they redesigned her study into something longitudinal. And these are the data. These are her data. So we're using weeks 2 through 8 to get rid of any effects of reactivity. So we're studying 7 weeks of data. In these trajectories, it's common to have sort of a thicker line that shows the mean trajectory. So what kind of slope does this look like to you? Is there a slope here? Nope. No. And there shouldn't be. This is not a treatment study. These are people who just, some weeks are good, some weeks are bad. On average, this is a measure of psoriasis severity where higher means worse. On average, people are about here, but as you can see, some weeks are better than others, and some people are just sort of more constant. So let's see, first off, how useful this longitudinal design was to her. Here is a little description of all the procmix commands that we're going to use in here. So this is just extra notation for you to decide what each of these things means. Let's start off with the Jeggings model, the simplest possible model that you would ever entertain for any data set. Empty means E only. So in this example, because we have a pattern where there's no change over time on average, we have no effective time in the model. We don't need it. But we still have to worry about what the right pattern is for the variance and covariance of this outcome over time. So it's the latter that we're focused on. What is the pattern that we want to have approximated before we go and add predictors? That way they get tested as accurately as possible. So here's the simplest option in the world. This is the worst possible model you could ever have. Ever. Do you know why? There's literally nothing in it. Empty means, so severity is my outcome, equals nothing. The slash is where the options start. In terms of the model for the variance, what are we saying about the variances and covariances over time? We're telling it that each person is measured repeatedly over weeks. And because there is missing data in this data set, week is important to put here. That way it knows which row to put each observation in. Type equals VC stands for variance components. In the book, I talk about that as E only. You can think of it as the regression version of the model. Variance is the same all the way across weeks. No covariance whatsoever. E only. So this is my R matrix that describes the variance and covariance the model says it should have across the 7 weeks. My fixed intercept is the grand mean outcome. So this is on a log scale, so the numbers aren't terribly intuitive, but 1.4 is what we have. So that's the model that isn't even on the list because no one would do it for longitudinal data. I just want you to have it as a point of comparison. So let's go up to here. Let's go to skinny jeans. So we're going from jeggings up to skinny jeans. Compound symmetry. Everything else is the same. Type equals CS. Try and get all of this on the screen at the same time. So the model parameters themselves, lost my mouse here, are right here. So in the output, you will always get what the model is estimating to make the patterns in a list. Here it's called covariance parameter estimates. It will be called something very similar across programs. How the pattern is made, you can find out if you also request that the pattern be printed. So sorry, my mouse keeps going to the wrong screen here. Come back here. Come back here, Mr. Mouse. Right here. Those two options ask it to print the predicted R matrix, which is the variance and covariance across weeks, as well as the correlation version of it. Okay, so the top one here, R, this is variance covariance. The diagonal is the same all the way across because that's what compound symmetry says it has to be. Skinny jeans are unforgiving. The variance at each occasion comes from two things. U0, mean differences between people at level 2. That's this number right here, this 0.68. And within person variation around those means, the e's at level 1, that's the 0.13. 0.68 plus 0.13 gets us to the diagonal of 0.8. The off diagonal is the covariance. Do you notice a pattern of what it predicts the covariance to be across weeks? Same. So no, I'm saying predicts. This is not reality. This is what the model says the data should look like. So let's think about this. If I have a skin condition and I'm trying to make it better, hopefully by some sort of treatment, that's where she got these people from, they were being treated by a dermatologist. Is it reasonable to say that how related my skin is from week 2 to week 3, which is the first two columns here, is the same level of relationship as the first week to the last week? Probably not. You'd think the weeks that are closer together in time would probably have more of a relationship. So this seems sort of implausible in the covariance aspect. The variance aspect seems probably pretty reasonable. If there's no change, then it's pretty reasonable that people would stay about as spread out from each other across weeks. So it's the covariance that we're going to be worried about in this application. If I take this covariance of 0.68, that's this number down here, and convert it to a correlation, that's the number that shows up in this R core. And that correlation of 0.84 has a special name. Give me an I.
Aye.
I. Give me a C. There we go. ICC, intra-class correlation. And now you can see this more readily. This is the average correlation of occasions from the same person. On average, the weeks are correlated with each other, 0.84. So what this model is saying is that the only reason the weeks are correlated at all, the only reason for the covariance is the random intercept variance. The only reason that weeks are correlated at all is because some people start out higher than others and they stay that way. Constant correlation, constant dependency due to mean differences. Thank you. Thud for emphasis. The other way we can think of that correlation, 0.84 is a ratio. 84% of the total information in the severity outcome is drum roll please, you got two choices. Let me get out our vocabulary scorecard from last time. Which of these two columns? 84%, the intraclass correlation of 0.84. 84% is, which one? Between or within? Take a vote. You vote for between? Who votes between? Anyone vote within? Abstain? Few abstain. Betweens, yes. 84% between level 2 inter-individual mean differences captured by a random intercept. Now let me stop at this next one. Cross-sectional. Now think back to my friend. She wanted to do a cross-sectional study and her committee thought, no, it needs to be longitudinal. She's 84% right. Her longitudinal study was an 84% waste of time. She could have gotten 84% of the information by measuring them once. Suck. But then I wouldn't have this lovely class example, and so that's really all that matters, right? I got to help her administer this study, so longitudinal studies are a lot of work. So most of the variation in psoriasis severity, which is our outcome here, is because some people have worse psoriasis than others. Yeah.
I guess it's still valuable because we didn't know whether or not it changed over time.
Well, how much it changes over time in the absence of any sort of special treatment. Yeah. Yep, you could spin it that way. You've still got 16% of the variance up for grabs. People do vary from their own selves, as my son would say. I'm going to do it by my own self. That sounds perfectly right to me at this point. By my own self. It's a combination of on my own and by myself. I'm doing it by my own self. Yes, people vary from their own selves 16%. That's something. It's not nothing. So 84% level 2 between, random intercept, 16% level 1 within. So, is skinny jeans better than jeggings? We don't have to do anything special to find that out because that is the one piece of information that SAS does for us. Stata also does this, by the way, automatically. I don't know of any other package that does, but it's possible you could get it out of R. I'm quite certain someone's figured this out. Likelihood ratio test. Comparison of model fit. So we talked about this last time, just to review. This number right here, 1049.7. Do you have any intuitions about that number of being good or bad? Nope, and you shouldn't. No idea if that's good or bad. It's only good or bad in relation to other numbers that capture model fit for the same data. So without U0, it's 1999.9. With U0, it's this. Likelihood ratio test is the model with fewer parameters, that's the previous one, minus the model with more, so that the difference is positive. So this number right here is -2 times the log likelihood for the sample. It is sometimes referred to as deviance. So you can think of this as deviant behavior being bad. Smaller is better. We want to minimize deviant behavior. So the difference between these two models is 950. The difference in log likelihoods, once you multiply it by 2, follows a chi-square distribution, approximately. So we added one term between the two models, that U0 variance. If you look up a chi-square table, anyone have the chi-square table memorized for 1 degree of freedom? What the critical values are? I do. I do for this one. For 1 degree of freedom, it's 3.84. 2, 5.99. 3, 7.82. 4, 10.49. I got tired of looking it up. Nowadays, you can use a function in Excel or any software package to get an exact p-value. But I don't have to get an Excel function out because a chi-square of 950 on 1 degree of freedom, yeah, we'll call that significant. In other words, the model that has U and E in its variance parameters fits better, significantly, than the model that has E only, chi-square of 950. The effect size for that comparison is the intraclass correlation. More specifically, 84% of the variation is U0 variation, and that's why we need that parameter in the model. The ICC of 0.84 is significantly different than 0, significantly greater. So this is just an entry point into longitudinal modeling. Wouldn't it be nice to know what the right answer is? Let's find out. That's the next model. We can fit this model in this case because we have enough people to estimate all possible variances and covariances for 7 occasions. That's 28. We have 124 people. And by enough, I don't mean like good power, I mean literally it would run. If you don't have enough, you will get a piece of output that says covariance parameters at last iteration. And they will have no standard errors and you will be missing the rest of your output. That means I gave up. That can happen if you try to estimate too many parameters with too few people. But we got it. Do you remember the other reason why this is possible to do? Think back to cooperation. Balanced, yes. People were measured weekly. And for the most part, they stuck to it. We paid them, so that always helps. And do you know the game Where's Waldo? Have you heard of this before? It's like a find a character game like in children's books where it's a really complicated picture and you have to find a little guy with a red and white striped hat. Well, I like to play my version of Where's Waldo, which is find the difference in the code that made this model different. Because sometimes it's like searching for Waldo. It can be hard to tell. Type, that's it. 2 letters. Everything else is the same. Just a brief aside here, I'm using a programming macro variable. Like this was like elsepath. This is an abbreviation for the name of my data file that I had defined up above. That way, if I change the name of the file, I don't have to change it throughout the code. So data file is a reference that was already defined. But yes, type equals UN. What does UN stand for? Unstructured. What kind of pants are these? Sweatpants, because they fit perfectly. You don't have to worry about not fitting. Sweatpants got your back. This is the data. This is the answer. This is as good as it gets. In terms of -2 log likelihood, that is. So if we look at the patterns here, variances along the diagonal, mostly the same. a few deviations from that, but nothing in any sort of systematic, it gets bigger over time or it gets smaller over time. If we look at the correlations over time, they are pretty high, but there is some variation there. So on average, the correlation over time was about 0.84, but you see that that goes all the way up to 0.92, all the way down to, let's see, 0.74-ish. So this is the model. And if I had lots of people and maybe 2, 3, 4 occasions, I'd be like, use this. It's the best one. You can't go wrong. But in cases where you have a whole lot of parameters to estimate, this can be wasteful. And if you can get by with something simpler that fits not worse, then ostensibly you have more power to detect the effects in the rest of the data set that you'd be interested in. So we're going to see if we can find something that's simpler that reproduces this pattern. So we're looking for two different things here in terms of reproducing the pattern. Variance is the same across time or not. In other words, the structures that we're going to look at are either homogeneous variance or heterogeneous variance. There's no intermediates possible in these choices. That comes next week. But for now, they're either all the same, homogeneous, or all different, heterogeneous. Unstructured is a heterogeneous. Compound symmetry is a homogeneous. Likewise, with the pattern of covariance or correlation over time, this is where we get kinds of different. Either it's all the same, that's compound symmetry, skinny jeans, all different, unstructured sweatpants, or different in some kind of predictable pattern. So now we're doing the patterns, okay? That's next. What are the predictable patterns that we can try? And we started talking about these at the end. So I will remind you of some of the choices here. First, there's compound symmetry heterogeneous. We could try that one. Here's a new one that we haven't seen an example of yet, but I talked about it. AR1 stands for autoregressive. Do you remember what kind of genes these are? Stacy and Clinton say they're the bad kind. Do I have to get up on the table again and demonstrate? But yeah, I had to sort of make them into cropped, but tapered. Yeah, so if you didn't have genes that tapered enough for your liking, you could taper them yourself by rolling them and making them real tight at the bottom. That's what I was demonstrating. Yes, tapered genes that go real narrow at the ankle, but they fit regularly otherwise. And why they look terrible on a person is because they make your butt and hips look way bigger than they need to be because of the narrowing. Why this looks terrible on a data set is because they predict that the correlation narrows way too much too over time. So the model itself looks like, so here's how it would be described if you looked it up, say, in the SAS user's guide for proc mixed. You'd see a pattern that looks something like this. So on the diagonal, total variance. So it's not trying to make U versus E. It's not separating things into level 1 or level 2. It's keeping everything together and saying that there's only one parameter for the variance. It stays the same over time. Now the covariance is described by only one parameter. What happens to it depends on how far apart the occasions are, or what's known as a lag. So occasions that are 1 unit in time apart. So 2, 1, 3, 2, 4, 3. Everything that's part of this first off diagonal They are related by a parameter that's estimated that's R. The next off diagonal, 2 units apart. So 3, 1, 4, 2, what would be 5, 3 if we kept going? It takes that same R that we already estimated and squares it. So it's not a new parameter, it's just an exponent of the one we already got. Likewise, 3 units apart, R to the third. 4 units apart, can you guess? R to the fourth. Is there a better way to say R to the fourth? Like you can say, like, square it, cube it, fourth it? Is that a thing? How do you fourth it? No? I couldn't come up with it. Fourth it, fifth it, sixth it. So the number of units apart in time is what the model says the correlation should be. And you can ask for a heterogeneous version of this as well, which just changes that the variances get to be different over time. So let's look back at how this would play out in these data. So where's Waldo? Here he is, AR1. Covariance parameters, 2. So this is a model that does not necessarily require that you have balanced data. To fit it using AR1 does, but there is another version in SAS that uses a spatial power structure instead that can be used for unbalanced data. I have a note about that somewhere in the slides. I can dig that out here in just a second. But here's what these 2 parameters are used for. So the first one is the easy one here, residual. Now SAS is not helping you. I told you that E variance is residual. What it means is actually total variance, because there's no other variance component to differentiate E versus U. It's both together. It's total. So in these handouts here, I've got my notes out to the side here that's trying to help you figure out what it actually means. So on average, the variance across people at each occasion is 0.8. So that 0.87999 shows up everywhere along the diagonal here. The other parameter, the AR1 parameter, is a correlation. So the R core matrix shows us how it gets used. So here's that R value. Let's see if I can highlight. There, it's letting me do it. Hooray. Almost. Hang on. That one, that one, that one. Okay, they're all the same, not a coincidence. They are 1 unit in time apart. So R is the correlation of occasions 1 unit in time apart. 0.8955 squared is the correlation 0.8, 2 units in time apart. 0.89 to the third is the next one. 0.89 to the fourth, to the fifth, and so on. So if you look at the last lag, the correlation that is 7 weeks apart, it says that by then, the outcomes should only be correlated 0.5. So it dies off quickly. But if we look at the original data, the unstructured matrix, the correlation is actually 0.8 still. It dies off too quickly. It narrows down your leg too quickly. So it's not flattering. That's where I'm going with the tailored pants. Tapered, excuse me, not tailored. Question?
So if our data set wasn't large enough to use the unstructured model as like the baseline, how else could we ascertain like a ground truth? Or
You don't.
you don't?
Nope. And the same thing happens anytime when you don't have a covariance matrix to come back to as the answer key. What you can do is start from the worst model and go up. And you never know if you've gotten to the close enough model because there's nothing on the other side to compare to. But you can just keep going and going until you're adding stuff and it doesn't help. And then you're like, I think it's good enough.
Okay.
But yeah, you don't. There's no real way. So everything is nested under unstructured. So we can do a likelihood ratio test to compare the fit. And there is an Excel sheet that goes along with this handout where I have recorded all of these fit statistics and their differences for you. So here was the unstructured model, and here is AR1. And here is, let's see, do I have, yeah, the test is down below. There's the difference. It's significant on 26 degrees of freedom. So in terms of fit, AR1 does not do as good a job as unstructured, according to the absolute difference in fit here. But look at AIC and BIC. Do you remember how to read those? Smaller is better. No cutoffs though. Which model does AIC like better? It likes unstructured. Which model does BIC like better? Likes AR1. This happens all the time. They will disagree with each other. BIC likes parsimony. BIC has a correction in it for not only number of parameters, but also sample size. It wants the model to be more better as you add things to it. So it is not happy that it took 28 parameters to get this much more better than 2. There's also a comparison here between unstructured and compound symmetry. That difference is 156. So this tells us something. Compound symmetry and AR1 have in common that they say the variance is the same over time. They differ in what kind of pattern they say the covariance has. Compound symmetry says same covariance across time. AR1 says it declines over time in this exponential pattern. The fact that same fits so much more worser than exponential, yeah, technical term, worser, means that we're heading in the right direction with some kind of covariance pattern that changes over time. It's not exponential. So let's see another one. Toplets, also known as banded. That's a synonym that you will read. TOEP 7. What does 7 mean? 7 refers to the number of bands that have separate parameters in making this pattern. So if you come down here to the number of parameters, there's 7. So you can think of it that way. Do you know why I can have 7? Because I have 7 occasions. I have a 7 by 7 matrix. That means that I have 1 diagonal and 6 off diagonals. So I am giving each, I can't call it row, each diagonal or off diagonal, this thing, its own parameter. So the diagonal, that's my total variance, estimated to be around 0.8, so the models are agreeing that that's about what the total variability is over time. It says residual, but it means total. These things then are covariances. So TOPE 2 refers to this number, which is the covariance. It's the second, I don't know, line? Can I say line? I'm coming up with vocabulary. Because diagonal doesn't work because there's only one diagonal. These are off diagonals. Like line. You know what I mean? Can I just do this and do line? People at home, I'm holding up a diagonal arm. So the first line is the diagonal, that's my variance. The next one, the first off diagonal, is covariance between adjacent occasions, 1 unit in time apart. The model says that any occasion that's covaried 1 unit in time apart, that covariance is 0.72. Likewise, any occasion that is 2 units in time apart. Come back, Mr. Mouse. Keep losing it. There, wait. There we go. It's back. 2 units in time apart is 0.69. 0.69 has no relationship to this 7.2. It's a separately estimated parameter. Likewise, another separately estimated parameter is for 3 units apart, 6.5. 4 units, 6.4, and so on. So I had called these boot cut, because in my experience, boot cut pants can either sort of flare at the bottom or they can actually just be straight. So the bottom can kind of, change to be what it needs to for the data set. So these are covariances. When you convert them into correlations, you can see in a more absolute sense what it's predicting. And it seems pretty reasonable. It seems like it pretty reasonably matches what's in the original data set. Still a strong correlation at the highest lag, but it does change over time. So this Topolitz model and the previous AR1, what has to be true about your measurement design in order for this idea of lag to work? Because I keep saying 1 unit in time, 2 units in time, and pointing to the different cells here. What has to be true for this to make sense?
The time lag has to be equal?
The time lag has to be equal interval. If I had follow-ups at 1 month, 2 months, 6 months, then this makes no sense. Because then I would have 1 and 2 is as related as 2 to 6. So equal interval, to use autoregressive or banded in this form. So relative to unstructured, we're so close. Look at that, P of 0.047. So riddle me this, folks. Do I want this to be significant or no? What are we doing here? I started with my sweatpants, most complicated, best fitting model, and I'm trying to find something simpler that does as good a job. So, do I want this to be significant? I don't. So this is a type of hypothesis test that is taking away parameters. When you take away parameters, your model has to get worse. The question is, does it get significantly worse? This is analogous to the chi-square test in SEM for whether your factor model fits the data. Not worse is what that test is asking. So this is marginally worse, right? In other words, I spent 7 parameters, whereas unstructured spent all 28. I saved 21, and my chi-square went up by 32. So a chi-square distribution on 21 degrees of freedom, that number gives us an almost not significant p-value. One thing that we can try to make it fit just a little bit better is to let the variances be different over time. So that's the next one, TOPE H. Any guesses what the H stands for? Heterogeneous, yep. Unfortunately, the other option, homogeneous, starts with H also. But that's the default. So here's what the pattern looks like now after we Hify it. What H does is give each variance a different estimate over time. So our previous homogeneous variance model said all of those diagonal numbers are supposed to be 0.8, one thing. This model says, no, all 7 get to be whatever they want. So those are nested. The number of extra parameters that I've added in making the variance heterogeneous over time is 6. I went from 1 variance that every occasion shares up to 7, each occasion gets their own. In terms of the predicted covariances over time, where's my mouse? I keep losing it. Here we go. Anytime your variance changes over time, your covariance has to change too, just because of that. So because of that, to get at a more accurate representation of how the occasions are related, this model is specified in terms of correlation. So in the output down here, you get the variability at each occasion. That's the total variability. And then you get TOPE H1. That's the correlation between occasions that are 1 unit in time apart. TOPE H2, 2 units in time. The model then takes that correlation, multiplies it by the standard deviations for the variances of those 2 occasions, and creates a covariance. In this case, we can do 2 different comparisons to see if we're heading in the right direction. First, does letting the variances be different over time help? Adding parameters. If we go from homogeneous to heterogeneous, from 1 variance to 7, does that help? Change of 6 degrees of freedom? Change of chi-square of 4.5? Nope. So that single 0.8 that we had before, good enough. Letting 0.8 wiggle around across time didn't help. And the other one, is this model not worse than the unstructured model? Nope, it is worse. So we added parameters to make it more complicated, but that led us in the wrong direction. Didn't help. Okay. So what all of these choices have in common, with the exception of skinny jeans, this is going to kill me. Come back, Mr. Mouse. This is why I don't have 2 monitors on my desk. There we go. Insert, insert. Stop. Insert, insert. So I'm adding in here AR1, TOPE. These are intermediate alternatives between these. So unstructured AR1 and topelets have all of the variability and covariability in one matrix. They don't use levels to try and make the patterns. The only model that uses levels to try and make the patterns is this compound symmetry, which pulls apart the total variance into 2 kinds. So what if we go back to this and start from here? What if we go back to compound symmetry, U plus E, and start from there? Turns out, that's going to work a lot better. So that's the next set of choices that we get to talk about next time. The so-called random intercept plus something else models. These options here, AR1 and Topolitz, these will show up in every longitudinal book that you will find on the shelves. In real data, they're not that helpful. So I include them here so that when someone says, did you try an AR1? You'll know what they're talking about. What's coming next will be more useful in most cases. It's based on this skinny jeans as a starting point, but then taking this E variance and saying rather than E's independent with constant variance, what if E needs something else? And it turns out trying to find a pattern for the E's is going to be way easier than trying to find a pattern for the whole thing at the same time. So in your homework, you will have sections, I think it's all the way up through almost the end that you'll be able to do now. There are models that say random intercept plus something. If the question says that, that's what we're getting to next time. So there's just a few questions about that. If you want to work ahead, that's the last half of chapter 4. So you should be able to complete your homework if you want to work ahead. Otherwise, we will talk about it next time. So, questions before we adjourn? Yeah.
I guess if you're suggesting that AR1 isn't very useful for most of our purposes, what class of problem was it invented to deal with?
Not people. Not people is my best guess. My guess is that it's animals, plants, or something where individual differences are not as prominent. Because the problem is that, like, if you measure somebody today and you come back a year from now, it's still going to be related. Whereas, like, if it's a plant, it may not be. And the fact that there's this constant force of correlation because of the person that you are, it doesn't anticipate that and it can't handle it. Topolitz can handle it, but it takes a lot of parameters to do so. So that's where it starts to break down. But yes, a lot of other stats books don't use people as their examples. They use pigs, plots, plants, amoebas. So AR1 might be fine for them. I'm just in the wrong business. I use people, in my studies. Other questions? All right, then office hours start now. If nobody is here visiting me, I will head back upstairs to my office. See you Thursday.